right, guys, so welcome back. We are continuing on with covalent bonding, and today we're going to be talking or focusing primarily on naming covalent compounds. As you might remember, in physical science, you might have done this once or twice before. We do have a prefix table, and you'll find that in your notes here in a minute. I think I have it in one of the bottom parts of your notes. But we're going to start today off talking about van der Waals, okay? So attraction between molecules. So a lot of times we talked about ionic compounds and how with ionic compounds the attraction has to do with the ions, right? Positive and negative charges. So unlike charges attract and they bond together and they stick together. But what really holds a covalent compound together? Okay, so that's what we're looking at today. What is holding these bonds together, and how do we name them once they form a compound? So the two weakest attractions between molecules are collectively called van der Waals forces, named after the Dutch chemist Johann van der Waal. Okay, now what's happening is these hydrogen bonds are attractive forces within a hydrogen covalently bonded to a very weak electronegative atom. It is also weakly bonded to an unshared pair of another electronegative atom, okay? And this is actually what forms water, okay? So the relatively strong attractive forces between water molecules cause the water to form small drops on a waxy surface. So if you ever see dew in the morning, okay, you'll notice these water droplets, and that's what they're coming. That's where the droplets are originating from. It's these van der Waal forces, these very weak electrostatic forces or electronegative forces that are holding these atoms together and forming where they're attracting to other water molecules. So it's not just within themselves they're attractive, but then because water's a polar molecule, water molecules are also attractive to other water molecules. So it kind of perpetuates this odd thing that water undergoes. And that also has to do a lot with why the density is the way it is, and also how ice is one of the only solids that floats on its own liquid form. I don't know if you guys knew that or not, okay? It has a lot to do with these intermolecular forces and these bonds within the covalent compounds, okay? Now, we're going to be moving into naming binary molecular compounds. Remember, binary means two elements, okay? We're going to start off with that, and then we're going to move into multiple ones, okay? So a prefix in the name of a binary molecular compound tells how many atoms of an element are present in each molecule of the compound. Now, where this is going to be a little different than from before, when we're dealing with ionic charges, we have that switching, right? The switching of charges, and we'd have to uncrisscross and things like that. You don't have to do that in covalent compounds. Actually, the prefix goes with the number that is associated with that atom. So the subscript written at the bottom will demonstrate the prefix you will use in naming, okay? So here's your prefix table. So if there's a 1, it's mono. 2 is di. 3 is tri. 4 is tetra. 5 is penta. 6 is hexa. 7 is hepta. 8 is octa. 9 is nona. And 10 is deca. Okay? So let's try to name a few of these. Okay? With these certain guidelines that we have. Okay? First of all, you will name the elements in the order listed in the formula. Same as ionic. Okay? And what also is going to be the same in the ionic is when you're writing the name, the first element gets its original name, kind of like what we did when we were talking about ionic compounds, when we had like NaCl. Do you remember how the Na just got sodium, but then the Cl changed to IDE? Well, guess what? The same rule applies in covalent compounds. The first element will just get the element's name, the second element will end in IDE. Okay, and that's the way all of our binary covalent compounds are going to be. Okay, you will use prefixes to indicate the number of each kind of atom. Okay, now when you're writing the first name, so when you're writing it the first name, you will omit the prefix mono when the formula contains only one atom of the first element in the name. The suffix of the name of the second element will end in IDE, which is what I just told you a minute ago. So let's do some examples here, because it's easier to understand this if we just give you some examples and we can work with it that way. So what we have here is we have P4S5, okay? So the 4 on the phosphorus is going to tell you what the prefix is. So if you go back to that prefix table, 4 is tetra. So this would be tetra phosphorus, and 5 is penta. So 5 is going to be pentasulfide. Okay, so tetra phosphorus, pentasulfide. Now the next one is selenium. Remember, 1 means mono, but you don't write mono on the first element. So this would just be selenium, okay? Then there's a 6 on the F, which is fluorine. Remember, the second element gets changed to IDE. So this is going to be selenium, hexa for 6, fluoride, okay? Selenium, hexafluoride, okay? Next, you have Si, which is silicon, and you have a 2 by it. So it's going to be disilicon, and then the Br has a 6, hexabromide. So the next one would be disilicon, hexabromide. And the last one is SCl4. Remember, if it's a singular 1 on the first element, the mono does not get written. So this would be sulfur, and then the 4 on the chlorine would say tetrachloride. Okay, so this would be sulfur tetrachloride. All right, now as you can see, pretty easy. So you're going to get a worksheet following this in which you will be naming some of the common covalent compounds. Okay, I hope you guys have a good day, and if you have any questions, please don't hesitate to email me, or we could do a Google Meet through 0 hour or after school. Okay, thanks.